So thank you for coming, and basically MIT asked me to come and talk about how I interact with MIT. Apparently it's something that works pretty well, and they told me it would be helpful to share it. So Mark was asking me, where's this picture coming from? It actually represents the myth of Daedalus and Icarus. Daedalus is the guy who flew with his son from the labyrinth, and Icarus happened to go too close to the sun and crashed. Okay, but there's a kind of something, an insight here to be realized, and that is Daedalus is the epitome of the engineer. It's a very interesting myth. It's the only guy in mythology that is not related to the gods. He uses engineering to clean up the mess that many of the gods actually create. So that's a very interesting thing. The other thing is he told his son, don't fly too high because your wings are held together with wax, and that is going to melt and you will crash. He doesn't listen, and the message here is when it comes to technology, the temptation to get too close to hot air actually leads you to crash. Anyway, having said that, let me go more to the subject matter. And I'm going to tell you basically three stories, but before that, let me briefly cover what is the problem. So I work in insurance. Most people, when they think about insurance, what is coming up their mind is the tied agents next door knocking on their door with crazy hair. Okay, I maintain insurance is probably one of the most exciting industries in the world, and I'm very lucky because I work in reinsurance, which is probably one of the intellectually most challenging industries that there are. What we do is we insure insurance companies. That's a pretty arcane thing to do. Now, insurance is really being hit like everybody else, but in two very fundamental ways by technology, and that happens alongside two dimensions. The first dimension is insurance is a very Stone Age type industry when it comes to administration processes, meaning the manufacturing of the product is too costly, too human, too paper intensive. And that's why insurance is so expensive. That is set up to change, and technology will play a major role here. The other thing that technology does at the same time, it changes the nature and size of what we call risk pool. Basically changes what we insure. Two examples for that. One is automotive. More and more driving assistant features are being added to the car. That is moving the liability in case an accident happens bit by bit from the driver to the OEM. That is changing very fundamental way the entire risk pool. The other topic is around, other example is around cyber risk. Now, people think about cyber risk always in terms of malevolent attacks. I think we need to think a lot wider, but I'm going to cover that by accident a little better in my presentation. The message here is, believe it or not, 5 years ago, nobody was talking about cyber risk. And now everybody talks about, and we don't really know how to insure it. Anyway, the other thing that I think is relevant here is how is my industry interacting with technology and technology companies. The industry is really struggling to succeed here. We see basically three phases through the industry is going. The first one is what I call observation. That's when insurance people go to disruption conferences and the like. They come back very excited. They say, we need to do something, and then guess what? Nothing happens. So the next stage is that, okay, then we need to test the stuff, and so they create garages, accelerators, and the like. And they work for years, and they do prototypes and so on. And then you ask, where's the impact? And there's basically nowhere to say. And so we spent quite some time, we were struggling with the same problem, quite some time trying to figure out why. And we figured out that to move to the next stage, which is basically value creation, is that you need to be very specific about how you deal with technology. So if you come and say, let's do something with AI, it doesn't mean anything. But if you come and ask the question, can I automate some claim adjusting processing, then AI may be the answer to it. So that's what we call use cases. It sounds a bit pedestrian, probably is, but it took us a decade to figure that out. Anyway, so let me now come to 3 examples of how we have been interacting with MIT, and that goes back basically, it also covers my former job. Before joining Swiss Re, I was the group head of strategy at Zurich Insurance, and it was kind of around 2011, 2012 that technology came up as a strategic topic that needed to be addressed. And very early at that stage, I started interacting with MIT as one of the places where you go when you try to make sense of what is happening. I'm going to show you some pictures because, as I said, those stories are improbable. Those are basically pictures of historical documents. So it's all true what I'm telling you. So one big problem the insurance industry has, probably not only, is the so-called legacy system problem. So we have the insurance has been introducing IT systems fairly early in its history. And some of the systems date back 40 years, 30 years. They're still operational, they're still working. They represent a legacy that is very difficult to manage. We would like to replace them because they're pretty inflexible. We can't because it's very expensive. So to give you a feel, to replace the legacy system landscape of an insurance company in one country, you're talking about 600-700 millions. So nobody has that money. At the same time, legacy system is a real problem because the people who have built those systems and can repair and maintain them are getting older and older. Demography is playing against it. Those people are retiring, they're starting to die. And whilst everybody in the world starts worrying about when is the singularity moment gonna come and displace humans, we may be facing a situation where old crappy systems are breaking apart and nobody's around to fix them. So that procrastination, I think, is very dangerous. So, but anyway, my question was, we need to retool those systems. How do we do that? In a way that we can afford. And then something serendipitous happened. I was on a flight, I can't remember which one, but probably between San Francisco and Zurich. And I was watching this video called The Imitation Game. It's the film featuring the story of Bletchley Park and Alan Turing. There was a passage in that film where Alan Turing basically says, a problem created by a machine can only be solved by a machine. So, and that was what started entire. So that was the one inside. Then I came back home, and then by accident, this is real serendipity, there were 2 books on my desk. That was the time when I was trying to understand or to learn information theory. And so I was reading Shannon, as you would expect. And at the same time, by sheer accident, a book about old manuscripts and how antique text was basically reconstructed using certain techniques in philology. And I thought, look, maybe we need to reframe the problem. Let's think of this problem of being a linguistic problem of translation of the content of one system to another system, as opposed to just think the nuts and bolts of traditional IT. So with that question in mind, I came to MIT, not really knowing who to talk about. And I was meeting some professors, going to conferences and the like. And then Enrico, who happens to be in the room, was accompanying me one day, and we were in the CISL building, I think. And then I saw a shield. It says, Noam Chomsky. Is Noam Chomsky still active? And they said, yeah, he's active. Let's go to the secretary, maybe he's there. So we went to the secretary, and She said, no, he's not here today, but would come tomorrow. If you come around noon, you get in for 3 minutes. So I changed my entire plans. So, and then the next day, here we go, I got him for 20 minutes and asked him the question. And he told me, young man, you don't need universal grammar to solve this problem because computer languages are unambiguous by definition. So you can be reassured that translation can be accomplished. Okay, interesting. By the way, that's generated further insights later on that were really helpful when it comes to understanding whether natural languages processing is possible or not. But I'm not going to bother you with that now. Now, the next meeting was, again, an ILP organized meeting by Cherry. I think she's in the room. And she told me, you really need to go and meet Dimitris Patsimas. Okay. And she managed to arrange. Apparently, it's very difficult. And we went there, and he wasn't there. So after 20 minutes, he arrived. And he told me, take place before we even start the meeting. Please tell me by which measure you will deem that to be a successful meeting. I was kind of, what a welcome. And then I answered, well, if we decide to meet again. And I'm going to cover this point later, is I think really relevant. Eventually, we had the usual conversation that you have the first time. And then time was running. And then I told him, one last thing. I have this problem with legacy system. Can you figure a way to develop a machine that can solve the problem? He more or less fell off his chair and said, I should have thought about this problem. I think I know. So he came back a little later. So this is the solution. Don't ask me to explain it. But eventually he did. And actually that sparked a number of research pieces and activities that ended in the creation of interpretable AI. And so that was kind of, we solved the problem. Unfortunately, people in the insurance industry are too risk averse to really try. But I know that others, including MIT itself, has been using parts of that technology to solve the legacy system problem. So it works. Next challenge was actually emerging from a conversation. So one guy I always wanted to meet in person was Dan Dennett. And actually, it was Anthony, who's also in the room, heard about it and said, OK, let me see, maybe I find a way. So I had dinner with Dan Dennett, and I wanted to discuss with him a problem of philosophy. Again, it would take too long to explain that problem. He didn't think it was a good problem to talk about. I was very jet-lagged, as you can see. Anyway, at the very end of the meeting, he came up with something that was top of his mind. And this issue was, look, we have a problem in moral philosophy that maybe insurance can help solving. And that problem is, who is liable if a machine kills somebody? If an algorithm behaves in ways that is not expected to behave. So I left that meeting really thinking, maybe we should rethink completely how we think about cyber risk and how we structure it. And that was the outcome of that meeting. So I took on that challenge. 2 years later, that's where we are. That's how everybody talks about cyber risk, malvolent attacks. So in reality, that's one part. There's a second one is simple IT systems failures. And the story is very simple. The world is moving to machines. Machines are vulnerable. If they break down, some damage will occur. And it doesn't really matter whether it's the North Koreans doing it or any other reasons. Third one is what we now call algorithmic risk. Algorithmic risk is when algorithms, for whichever reason, do things they're not supposed to do. And that was the part that basically was triggered that particular conversation with Daniel Dennett. And that is having real consequences, the way we really think about cyber insurance going forward. Third one is another problem, which is if you want to automatize processes in insurance, and I think in any industry, but in insurance it's very critical, you need to be able to have a machine able to transcribe the content of such documents. That is the handwriting problem. And on that one, I've tried with many universities to talk about this problem, and they all told me, no, but that is an old problem, it's long solved. I said, no, but it's not a problem because people are not, the world is digitizing, nobody's using paper anymore. And whilst they were telling me that, they were taking handwritten notes on their iPads. I said, sorry, this is not solving my problem. So anyway, then I dig further, and what people told me was the real issue here is that in order to enable a machine to solve the handwriting problem, you need data sets. You need many data sets, many styles, and then eventually the machine will start recognizing patterns. But we don't have such data sets. We have too small a sample. And then I thought, well, not sure that's true. There's an incredible sample of data sets of all possible handwriting styles over millennia available publicly in the internet. And interestingly, not only that, scholars have done professional transcription of that available in ASCII code, meaning in 0s and 1s. So why can't we have the machine going back and forth between the handwriting that is available and the transcriptions, and then check every time and learn from trial and error. So finally, Dimitris agreed to look into it. And so we are right now in the process of developing a general purpose handwriting recognition machine. It's working extremely well, with in the range of 85% in total accuracy, but we're only at one of many steps that we're taking. Is much more to it than just the handwriting idea and manuscripts idea. But the one thing that is interesting is people have been using neural networks and the like, using a certain data set that is standard for everybody working on this problem. So with what Dimitris and his team has built, we got to an error rate of 18.9%. Then we fed the machine with the handwritings of Jeremy Benton. And the performance jumped from 18.9 to 11.6. And now we're going to do more and more of that and potentially further optimize. Anyway, what do we learn from all this? Those are improbable stories. And I think the first learning really is that interactions with MIT can be astonishingly productive. And I'm taking here the corporate perspective, but you could kind of flip 180 degrees and think about a startup or a faculty wanting to interact with the corporate world. So it's difficult, and the first thing you need is a good guide. And MIT is very lucky. I've interacting with more universities than MIT, but the ILP program is by far the best in the world. It really gives you a guide. However, whilst this is necessary, it's not sufficient. What you need is actually to know what problem are you trying to solve. Many people go to places like MIT, and for them it's like going to the zoo. Sorry. They don't know why they are there, apart from getting a general introduction. So you need to know exactly which problem you have. Then you need to be persistent, because it's not very easy to get the time of the people you want to meet. And maybe you have to wait 20 minutes in front of an office and don't give up, or you have to be lucky that Noam Chomsky happens to be at least on the following day, so that you basically have to only to move a couple of meetings. If something comes across serendipitously, take it. because it's much easier to have conversation with those luminaries about something that is their top of mind. So that was my case with Daniel Dennett. And finally, you need to invest time. You need to give something to be here. I've been spending here some 50 days in the last 3 years on this campus. Even more if I think about the preparation. And even more important is give something back. You get a gift, give something back. That's why I've agreed finally to this speech, but also, it's very interesting. I have the luxury of really traveling the world. So, when I meet people here, look, where have you been last week? Well, I was at Tsinghua. What are they doing? Tell me. And the same the other way around. So that is what helps deepening those relationships. And with that, I think I'm almost on time. Thank you for your attention.
We'll take one or two questions here, yeah. So what do you think is the next big challenge in the insurance industry?
That's your question. That's the one we're working on. I think the real big challenge in the insurance industry is to make cyber risk insurable. And we are pretty much at the beginning, not to say ground zero. Other people would claim differently, but the reality is that it's a different type of risk. The type of risk that we are covering in traditional industry is basically, we think of kinetic objects that are hit by something, a bomb, a storm, whatever, but they don't move. Okay, at least that one doesn't move. So then we look at past events, and we do some modeling, and sometimes they've been deterministic, sometimes probabilistic, but it's backward looking. Cyber there's not such a thing as a kinetic object. It's all moving parts, and it's forward looking, because past data are not really helping you. Meaning you need to think probabilistic forward looking. That's the end of actuarial tables, at least as far as cyber is concerned. So it's a very tough problem to solve.
All right. Thank you, Luca.
Thank you.